back. Okay, so main high-level goal, we want to get 3D models, right? We want to have stuff that represents digitally the real world, and ideally, it should look like the real world, but probably even more importantly, it should also behave like the real world. And I think 3D scanning is probably the one thing we have been working on the most, especially when the Kinect came out. One of our first papers there was doing real-time 3D reconstruction. This was this voxel hashing paper. So the idea there is basically you have an RGBD stream, you have RGB as input, you have depth as input, and you simultaneously compute the pulses between the adjacent frames. And you then integrate all the depth data into a shared volume, in this case, a truncated sign distance field. And then at the end of the day, you're going to get reconstructions like these. And yeah, probably for the last, I don't know, 10 to 15 years, we've been trying to make this better, right? We've been trying to get, better alignment between the frames. So there's a lot of like online SLAM methods that have worked. ICP methods and so on have been gotten better. And we also used a lot of AI methods to figure out how to complete these scans to make them look better. But no matter what we have been trying, it has turned out it's very, very difficult to use these scans actually for things like graphics, for things where you actually run simulations on top of it. So for a lot of applications, these 3D scans are simply not enough. And it turns out no matter what you're going to do, these scans will probably never going to look like an artist-created CAD model, right? Or like computer graphics content. So if you're looking on the left-hand side, if you're looking at 3D reconstructions, you see point clouds, right? You see reconstructed surfaces. And if you're comparing this to the right-hand side, where you see 3D content from video games, from artist-created 3D assets, there's just a fundamental difference how these things are made. And it's not only that they do look different, even if you look at the most recent works like Trellis and all these kind of 3D generators, you're going to see that these are kind of marching cube style meshes. So they all have like a triangle soup with a lot of triangles. And this stuff is not compact enough for a lot of downstream tasks. Like if you're thinking about with like video games, for instance, what's very interesting is people actually literally optimize the meshes for every platform. So if you have like a new Call of Duty version that runs on a PC, that's going to have different 3D models than whatever runs on a PlayStation. And the reason is simple, right? You have different hardware, you can support different number of polygons. And this is something that all the 3D reconstruction methods, they cannot replicate because they don't have the domain knowledge, what an artist has, like how do you design these models and so on. So in this talk, since we're talking about digital twinning, I want to just present the history in the last 10 years. How do we get from scans to something that looks like the scan by just looking up CAD models and retrieving them and aligning them? So the high level idea is, right, we just say, for the sake of this talk, I'm not saying this is always a good idea, but for the sake of this talk, we're going to give up on getting better 3D reconstructions. And what we do instead is we just go ahead and take the scan and we try from a database, find the best matching models and try to align them to respective scans. And this is basically what you can see here, right? You see on the left-hand side the scans, right? These are the 3D reconstructions we have done with our Kinect style scanning methods. And then we have a CAD database. It could be something like ShapeNet, but it could also be something like Observerse right now when you have larger data sets. And the high-level idea is you want to figure out how to retrieve the best matching object such that it matches for every object in the scene. And you want to figure out how to align it. So you want to retrieve a pose and figure out such that you get the best match. For the most part, we have been looking at 9 degrees of freedom here. So we have 3 degrees of freedom for rotation. We have 3 degrees of freedom for translation. And we typically also use 3 degrees of freedom for the scale. So we allow anisotropic scaling because it turns out if you have things like a couch, you can actually modify the objects to a certain level such that you can match it much, much more accurately. We've also had a couple of papers where we try to do much more. Like we also tried non-rigid deformations to make it match even better. But as soon as you do more than 9 degrees of freedom, you're gonna, kill the structure and so on of the objects. And at the end of the day, this is something that is undesired. So for the sake of this talk, the point what we're trying to do is we're trying to go from here on the left-hand side, figure out the right objects, and ideally make these objects at the end of the day, the whole scene composition, get a scene graph out of it and make this as close as possible to the real world. So it's kind of this digital twin. It's like this digital clone that is very close to the real world, but it's a very clean, lightweight CAD representation. And you might ask, why do we need it? Okay, we have obviously like a lot of big terms in robotics are now simulation ready, right? So you want to use these kind of things to run simulations on top of it. You want to have robots to interact with it. And you might also want to use it for some graphic stuff, right? And there's a lot of applications with this specific problem you want. And I'm going to talk a little bit about the history, how this has evolved and where we are, and later on also talk a few things what I feel are still missing. And we actually started looking at this roughly 2015. That's about 10 years from today. And the idea at this point was there was no deep learning in these methods. It was literally just figure out how to match objects from a database by handcrafted features. So in this case, this is actually the Stanford dining hall. So we took a bunch of scans there. So we reconstructed all their chairs and tables. And you will see in the early methods, it was literally only chairs and tables because that's the only thing in the feature descriptors we're actually able to match. And in this case, what we did is we basically looked at the sign distance field and we constructed handcrafted 3D descriptors on the sign distance field and then used this to go through literally all the objects in the database and then figure out which one is the closest. And then from the closest ones, we were aligning them. And at the end of the day, we retrieved and aligned these objects. And then if you overlay them, they should match pretty closely. So if you're looking here, right, you see this overlay here from the retrieved and aligned objects. They're actually pretty decently close here. This one was done on sign distance fields. And what I mentioned is at this point in 2015, the 3D deep learning community was kind of still at its infancy. So there was not a lot of stuff out there that could actually learn these feature matches in order to get good alignments. And this obviously worked to a reasonable degree. It actually worked in real time. So you could in real time do a 3D scan. You could go around. And as you did the scan, you actually saw these objects popping up. And you can also revisit areas where the objects didn't pop up in order to still get enough data and get the objects at the end of the day. And then we thought, well, okay, this was 2015, right? This was just deep learning became a thing. And obviously, the next big questions was, can we use learning-based methods to do the same thing? And it turns out this is actually not such an easy task, right? Because if you're looking very closely here, you see that the scanned chairs, for instance, in this case, they actually have a bunch of missing data. And if you just have a generic 3D descriptor or something like this wouldn't really work well because, the data distributions between the synthetic CAD models, what you have in your database, these shapes, they're just fundamentally different than all the stuff you have in a real scan, right? And so yes, so semantically, these are the same, but geometrically, they are very, very different. And this makes it from a matching problem not so straightforward. Because if I have a feature or something like this, they would be very different for these two things because the underlying data distributions are not the same. Okay, so what's the obvious thing? How can we go ahead? The first thing is we thought, well, we just train a feature matcher to learn the differences or learn the similarities between these distributions. And this is a paper called Scan to Cut. It's like 6 years ago already. So you see, we're going to go step by step to the present. And in Scan to Cut paper, the first thing we did is we realized, well, there's no data available to train a descriptor like that. So what we wanted to do first is we wanted to go ahead and align these CAD models at a larger scale, such that then we can train our favorite neural networks to do the matching. So the first thing, basically, what we had to figure out is create a data set that has the objects retrieved and aligned on top of the 3D scans. And then once you have that one, you can go ahead and train your favorite network to do that. And even this is 6 years ago, so the data in this case is still pretty relevant, but obviously the neural networks that we had used at the time, they've gone through a couple of iterations how to do that. But I want to talk a little bit about that. First, about the data, how we did that, how we actually did the alignment. And then finally, I want to talk about how we evolve the methods over time and how this gets better and better in terms of getting better reconstruction fidelities. So let's first talk about the scan to CAD data set. So the scan to CAD data set is the first thing we had to do is we had to look at what 3D scans are available. In this case, we used ScanNet as a basis. So ScanNet is about 1,500 RGBD scans done with bundle fusion. So this is like an online RGBD reconstruction method that takes the input frames, aligns all of its stuff together, does a global bundle adjustment, and gets you a 3D scan out. So this is our scan. And as a data set, we took ShapeNet, specifically took a subset of ShapeNet. I think we took like 8 classes or so. And what we did is we had an, oops. Okay. So in this case, we have a 3D scene. This is from ScanNet. And then we did the retrieval and alignment based on that, and then we got the respective output. What I want to show specifically is that the annotation tool. This is this one here. So it's a web-based tool. So you have here the 3D scan. You here on the right-hand side, you see for every class, you see a couple of suggestions. And we basically used the class label in ScanNet to give you already a few suggestions. And then we just annotated key point matches between the two, right? So if this key point matches here, this one matches here, and so on. And when you have enough key points, then you running a procrast algorithm to align that. And then, yeah, you see it here right now. This object here was now aligned. And then, you know, you do this basically one by one for every object. And this is like a whole scene here, right? So this is basically the high-level result. And it took basically for every scene, you need actually a couple of key points, right? So you need about 100 key points or something like this. You can also see the more key points per object you have, the easier it is to get a coarse alignment. So you have basically ground truth key point correspondences. You use those ones for procrast optimization, and then you have the alignments of the objects respectively. And what we did is in total, we annotated the entirety of ScanNet. So ScanNet is 1,500 scenes. These are the RGBD scans. These are the reconstructions. We have annotated in close to 100,000 key point pairs. So like 100,000 times we had to click between the two. We in total have about 14,000 aligned CAD models and about 3,000 unique CAD models. So some models were chosen again because, you know, they were just more similar. For instance, in a room like this one, you would want to make sure also that all of these chairs basically align to the same CAD model, which is kind of reasonable given that the physical chairs are actually identical between them. Okay. Then for the method, I'm going to go over the method because there's a few things that are really interesting even for today's network. So that network architectures, of course, changed, but some of the method ideas I think are still very relevant, and they can be also applied to other domains. So, but let's start with the simplest thing first. So if you're training this, you now have ground truth data where you have the CAD models and you have the scans, and you basically have quote unquote infinite correspondences between them because you can literally take the existing CAD model alignment and then sample the respective correspondences. Okay, so here's the 3D scan. That's the first thing. And then what we do is we voxelize the whole thing. So we treat everything as a 3D grid. And we have voxels for occupied and not occupied. And the first thing is we run a key point detector in 3D. So this one is very similar to like Harris key points for the SIFT matchers or SIFT key point detectors, except that it runs in 3D. So it looks at the gradients. So it basically detects corner points. And yeah, you have a threshold. You can say, oh, how sensitive it should be to the gradient variation. So in this case, you get a couple of key points. You detect those ones, and that's where you start. And based on these key points, you now go ahead and look for this key point, what is the respective match on the CAD model, right? So here we have the voxelization of the scene. This is from the scan here. And this one here is from the CAD model. So here you see the other key point, and you know that these two match. So if you took the key point from the 3D scan, right, you know the respective counter pair based on the user alignment that we have in our ground truth dataset. So now we have those ones. Then we have another one here. We have another one here. And we have another one, and so on. And then what we do is we basically take these pairs and we train a network. So the network now, what it does, it literally goes ahead, and for this key point, you take a chunk of the scene. So it's a 3D input. And from this 3D input, you then predict where this point should be. And this is just literally a softmax in the output. So you just literally have a softmax classifying which is the voxel where the key point should be. So you just classify which voxel that is. And this is from a training perspective relatively straightforward to do. You can also label smooth it a little bit, then it basically distributes a bit and makes the training a bit easier. And what you do then is for every point here, you do a match, right? You run a network pair for every possible combination here. And then at test time, you you get these key points. And then you're running an optimization on top of it. In this case, we're optimizing for rotation, translation, and scale. And then we can align the object, right? So assuming the network makes reasonable predictions here, you can then predict or like optimize the alignment respectively. And if you're taking the algorithm again as a whole, what happens here is for every CAD model that you have, for every key point in the scene, you predict this heat map. So you run this network for every key point, for every CAD model, basically. And then for every CAD model, for every heat map, you run this optimization afterwards. So this is very easy to train. It is unfortunately a little bit annoying to run because you basically have to go through the entire database, right? It's kind of, it sucks a little bit how to do that. So it's a bit slow, but it works very, very well. And this was kind of the first attempt to do this kind of scan to CAD alignment with a neural network. And if you're comparing this to other descriptors that were available at the time, so if you're looking here, this is the alignment accuracy. So alignment accuracy means the model that you retrieve and align has to be within a certain threshold of rotation and translation. I think it was like 10 centimeters and 10 degrees or something like this. So it was a relatively tight threshold. And like 38% in this case were successfully aligned and so on. And what's very interesting is, so these baselines, I don't know if you still know them, they're like FPHH and SHOT. These baselines are handcrafted through the feature descriptors. So they use some sort of histogram over normal distributions, and then they use those ones in order to find correspondences between the scan and the CAD models, and then you do the alignment respectively. And unsurprisingly, this doesn't really work because, again, the distributions between the scans and the CAD models is very different, whereas the learned methods here, they actually perform reasonably well, and you get pretty good results. This one is kind of the, if you think about the most, if you had like today, if I have like an undergrad student or so who wants to do some research with me, that would be a method. This is the first thing to try, and it makes a lot of sense to start this way. But you could also already get pretty good results. Again, if you have here the 3D scans, these are our predictions here, and these are the ground truth. So you see, for the most of the scenes here, the predictions are actually quite reasonable. This 31%, what I just said, is a little low because the thresholds are very tight. If you relax the threshold a bit in this evaluation, then you can actually go and get a higher number. But yeah, it's not too bad. It's not horrible, and it kind of was the very first start where learning-based method learned key point matching between two different distributions, meaning the scan and the CAD models. So this was cool, but the downside I already mentioned, this thing is horribly slow. So it takes about 10 minutes per scene to run it. The issue is the retrieval is just not very efficient. So in other words, what you have to do is you have to try out basically 400 random CAD models to just generate these basic matches here, right? And this is obviously a little bit unsatisfactory, and it would be great if this could be done better. So how can we make it better? And I think the big limitation, what I just described, was you had to go through all these key point pairs. So this problem was this loop over the key points is annoying because every key point you try to match, you have to run a neural network in order to do this heat map prediction. And so in this spirit, we thought, well, maybe it would be better to just do everything on an object basis and just for each object predict the correspondences directly in a feed-forward fashion. And we call this end-to-end alignment, but this one I'll get to. This is why it's an end-to-end. So the first big change what we made is basically for every object you want to make a feed-forward prediction. In this case, what you have is, again, you have the data set, the database here, you have a 3D scan here, you have an input, you voxelize the whole thing. The first thing is you do run an object detection now. So instead of running stuff per key points, we go and running it per object. So you get the bounding boxes here. Based on the bounding boxes, you do you compute a feature per object and trying to do the nearest neighbor lookup, which CAD model to choose basically in the database. And then one big difference is now that for every detected object, we're going to predict a heat map. Instead of a heat map, we're predicting actually correspondences directly. And these correspondences are called symmetric aware object correspondences. And what this is nothing else to say, since for every point on an object on a scan, you predict what is the coordinate of the aligned canonical voxel of the object, right? So the object is always, let's say, in a 0, 1 voxel cube, right? And you just predict literally which of the voxel indices is it for every point on the input. So the output is a 3D grid for every object, and you just predict for every voxel what is the coordinate in the cat. And this one is easy now because you just literally run this for every object once, right? Instead of running it for every key point once, which makes the whole thing a lot more efficient. And then with these correspondences, you run an alignment again. And with this alignment, you can then basically optimize where the, in this case, tables and chairs, where they should be. Okay, let me talk about this part here first. These object correspondences, they have a little bit more stuff to it. They are basically dense correspondence maps. It's very similar, actually, what Duster and these kind of things do between two frames. But this is just being done on a per object basis. And there's a little thing you have to still consider here is you have to collapse the symmetries because some objects, they are rotation invariant. So for these ones, you have to adapt the ground truth such that it doesn't care how it predicts it. And this is important. Otherwise, there's an ambiguous output, which would mean for the network, it would be very difficult to learn that. And this one, what you can see here, these are these object correspondences, basically. So you see, like, based on that, you can then, get the correspondence maps and then do the alignment respectively. Okay. And then there's one little other thing. What we did is we actually made this pipeline end-to-end differentiable. And this is a thing which we did in like probably 10 plus papers afterwards because this worked very well. And what I mean by that is you can actually differentiate through the alignment process. So through this procrust alignment, it's basically computing an SVD, right? And through this alignment process, you can differentiate through. These are all matrix vector operations, and you can just literally use your favorite deep learning framework to differentiate through the alignment process here. And this one actually helps quite a bit. So this differential procrust here basically tells you not which is the right correspondence, but it tells you then which is the right correspondence such that the alignment is minimized in an optimal way, right? So, and this one actually makes a massive difference. And we've done this like for optical flow later on in a couple of papers. We've done this for non-rigid alignments. And I think this is very neat that you can differentiate through optimization problems themselves, which is kind of cool because they're just a bunch of matrix operations. Okay, so the whole pipeline is we take a scanner's input, we have a backbone which encodes the whole scene. We're running then the object detection in 3D, kind of like mask RCNN in 3D. We get the bounding boxes. For each of the bounding boxes, we get a small voxel grid. For this voxel grid, we run these symmetry-aware object correspondences. And then based on these ones, we run this procrust, and then the objects are being aligned. Okay. So the input scan basically has then anchor centers, object detection, bounding scale. You have the cat retrieval for each box, the sock prediction for each box, and we have this differential procrust. And if you're looking at the results, this now looks a bit better. So here we see the scans. I guess it's a little bit hard to see, but you see the scan to cat, what we had before, made a few more mistakes, and we're doing a little bit better here. Here's a few more examples. And again, like you see sometimes with scan to cat, you had these kind of things happening. This kind of looks a little bit better here. Okay, and then accuracy-wise, if you do this ablation study, I think this procrust end-to-end thing is pretty cool. I like this a lot because you could do this for all kinds of different things, and it gives you a massive performance boost at the end of the day. And if we're comparing, and here's basically, this is without the symmetry, right? This is without the procrust, and this is just predicting the 9 degrees of freedom directly. This one, by the way, doesn't work. You cannot just predict the output transformation because for rotation invariant objects, it just doesn't know what to do because there's so many ambiguous results and the input features, they don't respect it. Okay, and then against the comparisons, what we had before, we had the scan to cat as a baseline, which is like 31%. This one is 50%. And it's not only better, it's also significantly faster. So from like 10 minutes per scene, this whole thing ran in a fraction of a second, basically. And you can, okay, here it takes 2 seconds, but this is like a super unoptimized way. You could get this easily under a second. This is very straightforward to do. So this is pretty cool. And this one works pretty fast on top of RGBD scans. And now what we want to do is we want to do the same thing, except we want to do this on images right now. So what I've shown you before, everything took a 3D scan, but it turns out the same pipeline, what I've just shown you with this end-to-end prediction, you can actually do on input images. So here the idea is the same way. So you just take an input image, and then you retrieve objects from a database, you get an instance segmentation with mask RCNN, and you predict these dense correspondences. So for every pixel, you predict these symmetric aware object coordinates. And then you run a differentiable per cluster optimization, same thing what I just said, and then you correlate it with the respective ground truth, right? So here you have, this one here is basically the input, right? And this one is the respective output, and this is the overlay. So, and you can do this on a single image, which is kind of cute because it has a lot of applications where you didn't have the RGB data available. So let me show a few results here. So this is an input image. This is the respective 9DOF alignment. And you see we're already at 2022. So it took a little bit more better networks to get this to work. But you get, in a feed forward pass, just forward shot, you get actually pretty good and pretty decent alignments. Okay, I want to show this again, right? So here's the input image. So you can see all the chairs, tables, monitors, and trash bin and stuff like this all gets aligned. Here's a few more of the examples here in the outputs. So you're going to have here the input scan, the input image, the overlay, and the respective geometry we also have at the end of it. A few more. Again, we did this in our lab, and I think this looks actually pretty cool. I can actually show a few more here as well. I don't know if this one works. Is this working? No. Yeah, okay. Maybe I should do this offline because it's a bit tricky with Zoom. Yeah. Okay, let's keep it this way. So this one was pretty cool. This was like 3 years ago. And the obvious thing here, if you look at these results, though, is it doesn't cover the whole scene, right? It misses like the wall structures. The other thing it didn't do anything with appearance. So it missed all the properties for physics. So a lot of people were motivated to use this for robotics tasks. They wanted to have some physical properties on top of it. And there have been a lot of methods right now to add more attributes to it. And I want to show one more method that basically goes back to the RGBD scan setting. So this was a collaboration with Cambridge. Jenning Hung did this actually. It's called Light Reality. This is a NURBS paper from this year. And here the idea is basically, if you're looking already, this is the output on the right-hand side. So this one is actually now, so on the left-hand side, this is the input scan, and on the right-hand side, this is the respective CAD abstraction. And you see, this one is actually the whole room structure gets now retrieved and aligned, and you see for every object, and you also get textures and material properties for everything. So this is like trying to make this a step further and actually make the simulation ready, so you have material properties on top of that as well. So this is how this looks. You have basically an iPhone in this case, so we just use the iPhone LiDAR data. You can move around. On the right-hand side, you see the scan, and this one is actually the reconstruction right now with this method. So you see like everything is being retrieved and reconstructed. This is the input scan, right? It's very noisy. And you see here on the left-hand side, you see the output of the method, which actually looks pretty similar to the input already. If you're going back here quickly, can I play this one again? Sorry, I'm going to go through this one quickly. You see here on the left, then when it's a side-by-side thing, it's actually pretty close to the input already, right? So this is the input. Yeah, it just respects the input very well already. Okay, so let's talk about this method. I don't have that much time, I think, but I wanted to just give a very brief outline here. So the input here is an RGBD scan. These are LiDAR reconstructions from the iPhone. So it's a handheld commodity device. First thing we're going to do is we're going to detect all the 3D bounding boxes. So we know which objects we have to retrieve. And from that one, we're going to do a scene graph. So we know which object is close to the other objects, and you have the relative transformations. You parse the scenes. And from the scene graph, then we want to figure out what are the objects that we need. In this case, we're using another CAD database here, right? We're figuring out based on semantic which object it is. And then we're doing also an alignment on every object for every bounding box. This is actually very similar to the previous method, except that these backbones now, they become much stronger, they're much more robust, and they can even handle the relatively noisy and incomplete iPhone data. Okay, so this one is basically give me a scan, detect every object, do retrieval and alignment per object. The next thing is we want to also get the material properties for these ones. So basically, we want to get textures. So first, we're looking at the albedo only, and then we using vision language models basically to figure out what are the right retrievals from a material database. So you have the BRDF properties in order to do relighting, shading, and all this kind of stuff. Yeah, and then finally, there's the layout reconstruction, which is for the non-object parts. Yeah, there's windows, doors, stuff like this. And the objects are being reconstructed. And then you have, in addition to that, you have a couple of other things that make things like simulation ready. So you have interaction properties like door can open, drawers can be opened, and stuff like that. So I glanced over this one quite a bit, but this is actually a pretty complicated system. There's quite a few things happening here in these stages, starting from the whole backbone that detects features and so on, to retrieve the objects, align the objects, get the material properties, and then make everything ready for interaction and so on. So I want to show a few more results here, because I think this one actually got quite some attention. This is probably one of the state-of-the-art methods right now for kind of creating a cat-like digital twin of a real scene. So here on the left-hand side, you see the RGBD input, basically. I mean, this is just the RGB input, obviously, but it has also the lidar depth. And then here you see the respective reconstruction. And if you're looking at this, of course, the objects are not perfectly the same. You see these tables, for instance, they're slightly different. But if you look at the whole structure of the room, right? 1 sec, if I can show this quickly, right? I mean, oops. So these tables here, right? They are like different. But like the couch and the windows and stuff like this, that's pretty faithfully reconstructed. And yeah, if you're going through it, yeah, you see basically you can now simulate the same camera trajectory which was recorded. And you see, yeah, I think this looks actually not too bad, right? Yeah, if I play this again, right? Okay, so the paintings, for instance, are missing, and the wall is a bit broken here, but for the most part, I think it got the scene actually pretty well. Okay, here's another example. This is on Scanet now. So here on Scanet again, you see like you can just mimic the virtual camera path, and you can see this is actually pretty well aligned right now. And I don't know, I think when I saw these results the first time, I think this was quite exciting. Obviously, it's not perfect yet, but I think it's pretty close actually, right? I mean, and you can do a lot of cool stuff with this one already. You kind of have a very abstract representation. And what I found interesting is basically, you saw these previous papers that just shown you like each of these little pieces, they are part of the system right now, right? There's like all the ideas that the community has developed over time, and has now managed to get, I think, pretty good results. One thing, obviously, what is still missing here is the objects are still not perfectly the same. I mean, one obvious future step would be something use like, Mesh GPT style generators or trellis-like generators to make this even closer. But then there is a risk again that it's not 100% a CAD model, right? So you have to balance this one out. And this one we didn't do yet. But yeah, you can take the outputs and you can relight them. So here's a reconstruction, right? Because this is now all graphics content. You have the BRDFs on this one. You can now change the lighting accordingly in the scene, and you can shade it depending on what you want to have. You can interact with the scene. This is an interaction example. So again, this is the reconstruction you see here. Now you can, do stuff with it. The drawers open, the doors open, the windows open, and you kind of have, kind of well, it's not perfect yet, right? There's still a lot of things missing to actually reflect exactly the behavior of the virtual world, but at least you have kind of a semantically sensible reconstruction of it. Okay, here's a few more of these examples. Basically, this is the reconstruction of a room. You can edit it, you can do stuff in it, and you have kind of this abstraction. Okay, with that, I would like to conclude. I think like in the last 10 years, basically, the first thing we started was basically take RGBD style scans. We mostly used some 3D feature descriptors. First, they were handcrafted, then they were learned, like scan to CAD, this end-to-end CAD, scene CAD. These were like the very, very first papers. They were kind of niche papers at the time, right? They were pretty small because they only could support a relatively small subset of the categories. And then, it became also feasible to do the same thing with RGB only stuff. Like, Im2CAD was probably the first one by Qishan. Then Roka, what I just shown you, this was one of them. And these ones basically exploited the fact that neural networks for 2D images became pretty good, right? You had pretty good feature extractors. You could detect stuff reliably and then align the objects. And yeah, since like the last 1 or 2 years, or 3 years, people are focusing really on entire scenes, right? You basically go ahead and want to have the structural elements, and people started with texture stuff and so on. And yeah, so the one thing I think what's still missing is basically that the objects are not perfectly the same, right? They would be great if we had more variety. I don't know, inverse procedural generators might be very interesting. And yeah, there's a couple of cool things to do. Okay, with that, I have one small thing I still wanted to do. I wanted to do some shameless advertisement for our startup. If you want to build things like these or build general vault models, at Spatial AI, what we're doing is basically go and take image and text inputs and build really big foundation models that create virtual worlds. And yeah, I think it's a pretty exciting time to do that. We also have a lot of resources now, so we can blow through a lot of compute and so on. So it's quite exciting what we can do now. And yeah, we are currently, I mean, it's already a bit outdated. We have like 13 people in total right now. And we are hiring across these things. So if you're interested in 3D stuff and foundation models, then we are a good place for you guys. Okay, with that, I want to thank everybody. Thanks again for the organizers to have me, but also very much thanks for all the people who did it. The original scan to cat stuff was mostly by Armin Avetisian. He was my first PhD student, actually. And then the later stuff was by Senning, who has been working remotely with us. And I think it was cool, and I look forward to seeing more stuff in these directions. Yeah, thanks so much.
Take a while to do your questions.
Yeah, so the question was basically whether you need to have the CAD model already for the object in the scene. So in this case, we're assuming that, so it's different strategies, obviously, how to do it. So here the compromise is you say, assuming you have a reasonably large CAD database, so Observerse, for instance, has like, I don't know, 10 million plus objects, you're saying, aside from scale and sizing, you assume you cover a reasonably large number of objects in a scene. And for indoor scenes, that I would say is true, because if you're honest, there's just N models from IKEA and so on, right? So there's not so many different furnitures. So for that one, it works pretty well. But if you go outdoors, it becomes a bit more tricky. For cars and so on, it still works. But for trees and stuff, it's very difficult, of course, then because they have so irregular structures. But yeah, we're assuming that we have at least something that is reasonably close here. There's a lot of work right now, again, that tries to do like mesh generators and so on. So we've been working on this a bit, but then it comes to the compromise that the meshes don't look so great anymore. Yeah, so I think the big question is basically how to turn Gaussian splatting into CAD models, right? So if you solve that problem, that would be very nice. I think the reason, I think we live in a little bit of a bubble right now. In the research community, everybody uses Gaussian splatting, and in the real world, not that much. And there's a reason for it, right? Because meshes are still pretty good for rendering. I think a GPU can render meshes very fast. Gaussian's reasonably fast, but too slow for games, right? So yeah, I think that's a worthwhile research endeavor, like figuring out to properly mesh the Gaussians, right? I think you can only do it with learned priors. I think it's very difficult to do it without that. But yeah, I think we're gonna probably see a lot of progress on this end. But yeah, in all fairness, like even NeRF and Gaussians, real world applications, not so much yet. So still a lot of research needed there.
Can you share a little bit of how related to 3D function model? For example, are you considering some kind of physical property or
Yeah. Yeah, so the question was whether I can share some of the milestones for building the 3D foundation models, whether we consider like physics and stuff like this. And yeah, I think so when I talk about this, I always mention I want to create virtual worlds or generate virtual worlds that look like the real world and behave like the real world. And this immediately gets you to the milestones, right? So first of all, we're going to get looks, then we're going to get good geometry, and eventually we're going to get interactions, and finally we're going to get all the physics stuff, what you need. For the looks, we're pretty close. That one looks pretty good. Geometry is kind of getting there. Interaction in physics is at its infancy. And part of the reason why interaction is so difficult is for static scenes, we're doing pretty well if reconstructing scenes where you can basically get a lot of training data for this stuff. for dynamic scenes, even the dynamic reconstruction methods, they're really bad. We see a lot of dynamic reconstruction methods for humans and so on. This works pretty well, like the simple stuff and so on. These kind of things work really well. But for like generic dynamic scenes, like even clothing and stuff, it's very difficult. And because of that, we have no training data for the foundation models yet. So we have to really think about how we train that. I think the ultimate training is videos because you just have so many of them. I don't think video models right now do it because they have no good space and representation to learn it. But I do think I do think videos is a good source probably to train it, and then you figure out the right representation learning and so on. So yeah, so milestones, appearance first, static scenes first, geometry next, and then finally you go into dynamics, interactions, and then we can do all the cool like simulation stuff and so on. But yeah, that would be amazing.